Astronomy on Tap fans. We are back. So, I hope you've gotten your pizza and your drinks. And it is my pleasure to introduce our next speaker. We have for you Malena Rice, who is a graduate student at the Yale Astronomy department. Malena's research interests include exoplanets and planet formation in general. And if you don't know what an exoplanet is, you are going to learn right now what an exoplanet is. And Malena is also an NSF Graduate Research Fellow. That is just an amazing honor to have her. And so, without further ado, Malena Rice on exoplanets.
Thank you for that excellent introduction. So I just want to test the sound. Is this okay for everybody in the back? You cool? Okay, awesome. So I'm going to be talking about exoplanets, as Yotam said. It's something very close to my heart. I absolutely love exoplanets, and I'm very excited to tell you all about why. I think they're like the coolest part of astronomy. And so usually when I tell people that I study exoplanets, they're like, wow, that's so cool. And then there's like this awkward pause, and they kind of like think about it for a little bit, and they're like, I actually have no idea what an exoplanet is. So just to kind of clear the air, I'm going to tell you guys what an exoplanet is. Oh, whoa. Okay, so exoplanet, noun, is a planet that orbits a star outside the solar system. So examples of things that are maybe or maybe not exoplanets are like these pictures here. So you have seen some of these pictures in Chris's talk, and one of them you haven't seen in Chris's talk. So the thing farthest to the left is not an exoplanet, that's Jupiter. So it's in the solar system, which means it's not an exoplanet by definition. The thing in the middle is unfortunately not even a planet, sorry guys, it's Pluto. So that's a dwarf planet. It got kicked out of the club and like some years ago, I don't know, I was in elementary school. And so Pluto is also not an exoplanet. And this last thing that you can like barely see is an artist's impression of an exoplanet. So we actually don't have any sort of like really high resolution images of exoplanets because they're really far away, so you can't just like take pictures of them casually. So this is maybe what people think an exoplanet could maybe look like. Alright, so we have about 100 billion stars in the galaxy and about 100 billion galaxies in the universe. And so just doing the math, that's like a lot of stars. And so we've always kind of expected there are probably a lot of planets out there in this universe, but they weren't actually found until like the 90s because again, they're really far away, they're really small, it's like a very tiny signal, and it's not that easy to just like go out there and find an exoplanet. And so the nearest star is 4.2 light years away, which means that if you travel at the speed of light, which is like the fastest you can possibly go, it'll still take you more than 4 years to get to the nearest star. And that's just the closest one. And so we think that there are exoplanets around all these stars, but then how do we actually go about figuring that out? And so the most successful mission that has found a lot of exoplanets is called the Kepler mission, and it was launched in 2009. And so before this, we had found some exoplanets. Chris talked about this a little bit, where you can detect them using like studying the gravity of the planet and how it's affecting the host star. And then there's also this other method that Kepler used that is how we found actually most of our exoplanets. So before Kepler, we only knew of like tens to maybe hundreds of exoplanets. And then after, we're now at something like 4,000. So there are a lot of exoplanets that have now been detected because of this super successful Kepler mission. And the way that Kepler works is that it just stares at this one spot on the sky, and it just kind of like waits for a really long time, like years. And let's see if it. Oh, yeah. So this is the picture of kind of like what Kepler is looking for. So it's just staring at the spot on the sky and waiting to see if planets will move in front of stars. And it was expected, like, you know, maybe Kepler would see some planets going in front of their stars. You really need a very specific geometry in order to see this. So what this plot is showing is just a planet is kind of going in front of its star and it blocks out a little bit of light. And when it blocks the light, then the brightness of the star goes down a little bit because there's something dark in front of it, and then the dark thing kind of moves out of the way, and then the light goes back up. And so Kepler was just looking at this little area on the sky and seeing like, okay, are we gonna see, like maybe we'll see some planets, we don't really know, it was kind of just an experimental mission. And it was just absurdly successful. So what this video here is showing is all of those dots are little planets that are found just over time. And you can look at the time scale up here on the right. And this is just looking at a week for this entire video. And there are just constantly these transits popping up all over the place. So this is Kepler's field of view, which is about the size of your fist if you hold it up against the sky. And that's how much of the sky that Kepler was actually looking at. And there are just these transits that are constantly happening. So we just keep seeing planets moving in front of their host stars and detecting like tons of planets of all different sizes, all different temperatures. And so Kepler was this crazy success, and we had no idea that it was going to be this successful. So it really launched the field of exoplanets. And what's really so amazing about Kepler also is that you really need a very specific viewing geometry in order to actually see planets transiting. So if your orbit looks like this, like that initial one where you can see a dot on top of the star, then you actually will see a transit. But if it's in any other orbital geometry, so if your orbit is kind of more face on, then you won't see a transit. So all those transits that we saw, they happen to have this correct geometry, which means that there are probably a lot more planets out there, even in just that field, that we just couldn't see because they didn't have the right geometry. So that's pretty amazing in itself, because we already found like 4,000 planets, and that's just like out of sheer luck that they happen to have the right geometry. And so this is another really cool video. I pretty much made this talk based on like really cool GIFs/GIFs that I found online. It's just like found some words to go with them. So this is a really cool video comparing the solar system to a bunch of the Kepler exoplanetary systems. So if you look here, the solar system is labeled solar system, as one would. And you can see sort of the inner planets that are orbiting just the center where it says solar system, and that's just the inner rocky planets. And so, first of all, one of the things that we can notice is that all of these little regions, I don't think you can actually see the orbits from where you are, but they're all orbiting their own stars, and it's just a bunch of different planetary systems kind of next to each other so that you can see them for scale. And something really incredible is that, first of all, most of these planets are really close to their host star. Like, the point that they're orbiting around is so close to where they are, and the circles they're moving in are so tiny compared to the ones in the solar system. And so what that means is that there are all these really exotic planetary systems where the planets are like right next to their star, and they're like so much closer than even Mercury is within our solar system. And the crazy thing is some of these are like really giant planets. Like they're Jupiter-sized planets that are right next to their star. And that's just something completely insane that we never even knew existed before. So then this kind of starts to raise the question of like, is the solar system a weird anomaly? Like, is it more common to find systems like this with like tons of planets that are right up against their host star, or like is it more common to find things like the solar system? And just as a note, this is also a detection bias, so it's much easier for Kepler to see planetary systems like this. But it's just kind of crazy that they exist at all, and that's why Kepler was so successful. And we didn't expect to find this because that doesn't exist in the solar system, so we didn't know that this would happen. So I'm going to go into just a couple of the really cool types of exoplanets that were found by Kepler. And the first one that I want to talk about is hot Jupiters. So hot Jupiters are kind of like those systems where you saw like these giant planets that were right next to their host star. That's what a hot Jupiter is. And these are somewhere between like 0.3 to 12 times the mass of Jupiter. So they can be really, really big. Some of them are almost the size of stars, and they're right next to the star that they're orbiting. So hot Jupiters have periods of like 2 to 10 days. They have a year that is like under 10 days. So they're just kind of zipping around in their host star in 10 days or less, which is totally crazy, and it's like something completely unlike anything we have in the solar system. And because they're so close to their host stars, they also have really weird chemistry. So we found weird things like titanium oxide and vanadium oxide in their atmospheres, and they're also much easier to study than other planets because they're so big. So they have really high signal to noise. And so we've been able to find like water, methane, CO, and other elements within their atmospheres, which is really exciting. And they're kind of the frontier of studying the actual composition of exoplanets. Okay. So moving on, another of my favorite types of planets that I think is super cool is super Earth. Planet 9 that was mentioned earlier, if it exists, would be a super Earth. But other than Planet 9, we don't actually know of any super Earths that are in our solar system, which is pretty crazy because they've been found to be actually super omnipresent in other solar systems and other planetary systems in general. So super Earths are really common, and Kepler found that, and they're kind of like the Earth except bigger. So this is like an example. So the name is sort of suitable, but there's kind of like between the range of Earth and Neptune. So some of them are thought to maybe be a little bit more like Neptune and more like gas giants, and some of them are sort of more like Earth. And that transition is at about 1.6 times the radius of the Earth. So if it has a radius larger than 1.6 times the radius of the Earth, it's probably kind of more like a gas giant. And if it is a little bit smaller than that, then it's probably more rocky. So super Earths are really interesting because they also have a much stronger gravitational pull than like regular Earth, I guess, if you would call that regular. And so as a result, they are able to hold in a much larger atmosphere. So they can have a thicker atmosphere because they have a stronger gravitational pull, which means that some people have referred to them as super habitable because maybe they could like protect from cosmic rays better. And they also would be a lot more difficult to escape from. So if you were on a super Earth, it would be a lot harder to get off of it because it has a really strong gravitational pull. So if you wanted to launch like one of NASA's spacecrafts into the air from a super Earth, it would take like 60,000 tons of fuel. So it's a lot harder to escape because it has such a strong gravitational pull. So that's something interesting. If there was life on super Earths, they probably would be pretty restricted to like ground-based astronomical observations, so they can't just like send up satellites all the time the way that we do. So this is a picture of a likely uninhabitable super Earth. Oh, it's a GIF. One of my many GIFs, whatever. And so I say that it's likely uninhabitable because you can see that it's like scorching and it's right up next to its host star. So that's kind of characteristic of a lot of the Kepler planets because they're really close into their host star. Yeah. Okay, so this is a topic that is kind of unavoidable when you get to talking about exoplanets because everyone kind of wants to know, like, are we going to find Earth 2.0 or like, do they exist? Are we alone in this universe, or is there other life out there? So I'll talk a little bit about some of the more Earth-like planets that we found, and just kind of give a little bit of background about at least what we know. So the short answer is like, we don't know if we're alone, but I'll tell you what we do know. So these are a couple of the rocky planets that were found by Kepler as of 2015. And these are around a couple of different types of stars. So these are like about Earth-sized planets. Here they are scaled up about 25 times relative to their stars so that you can see them. And G stars are like the sun. So the Earth is within that category along with Kepler 452b. And those are probably a lot more likely to be kind of similar to Earth because they formed around a very similar star. Whereas the other systems are, it's kind of like maybe they're similar to Earth, maybe they're quite different because they formed in a very different system. So in particular, M stars are commonly like studied in a lot greater depth because they are a lot smaller, so it's a lot easier to see planets around them because the planets are larger relative to the star, and so the signal is better. However, there's kind of a caveat there because M stars tend to be very active. They have a lot of UV radiation and there's a lot of stellar activity. So that may or may not kill all life that would exist on said planets. So there's kind of a trade-off, maybe there's just like a ton of extremophiles around M dwarfs on those planets, or maybe there isn't life, and that's kind of something that astrobiologists have been studying in greater depth and trying to figure out whether it's possible. Another cool result that came out pretty recently in the news, I think it was actually like a year or two ago, so it wasn't super recent, but relatively so, is the TRAPPIST-1 system, which is 7 rocky planets that were found around in M dwarf. And these were named after the TRAPPIST spheres, so it seemed kind of appropriate to talk about in this setting. And 3 of those planets are thought to be in the habitable zone of their host star, which means that they could potentially have water on their surface in the liquid form. So that's kind of a really exciting result. We don't know too many of these planets. Basically, we know like their radius, their mass, how long it takes for them to go around the star, and not that much more. But hopefully with upcoming space missions, it'll become more possible to actually learn like details about the composition and try to learn in greater depth about these systems. So looking towards the future a little bit, the Transiting Exoplanet Survey Satellite is an exoplanetary mission that was sent up this August. It was sent up like very recently in 2018, and it's now kind of in the calibration phase and it's starting to take data, but it is kind of like the successor to Kepler in a way, in that it's searching for a lot more of these transiting planets, and it's specifically looking for nearby planets around nearby stars, ideally as many kind of like Earth-sized planets as possible, because that's what people are generally most interested in. And what it's doing that is quite different from Kepler is it's actually looking at the entire sky. So Kepler just kind of stared at one little spot and found all the planets there, so a lot of them are really far away. And so even if we found out that they were kind of like Earth, they're really far away and hard to study. Whereas TESS is going to be looking at 85% of the sky. So here you can see its entire field of view, and that little thing up there is Kepler's field of view. So that's just like a tiny bit of what TESS is going to be looking at. These are the Kepler K2 fields, which is sort of a continuation of Kepler that happened after Kepler ended. So hopefully with TESS we'll be able to find a lot more of these planets and a lot of the nearby ones, which will allow us to kind of characterize them better because we'll have better signal to noise in general. And that image there is the James Webb Space Telescope, which is something that TESS will be kind of finding targets for, and that will also be able to look at the atmospheres of these exoplanets in a lot greater detail. Okay. So I talked a lot about all these transiting exoplanets, but we don't want to forget about all the other ones, because there are a lot of other planets that are not just transiting, and there are a lot of kind of cool results with the ones that are sort of a little bit harder to find. So I think that this is actually sort of the future of exoplanets, and this is something kind of close to my heart because I worked on it for my undergrad thesis. But we can also directly image some planets. So if planets are far enough from their host star, and if they are kind of bright and very large, then we can actually take direct pictures of them. So what you're seeing here is there's a mask sort of at the center that's covering up where the star is in this system. And that's called a coronagraph, and it just blocks out the starlight so that you're able to see what is around the star. And then you can see that these little dots here are actually planets. And so these are actual data images of a planet. This is not just like a GIF that somebody made to look fancy like a lot of the other ones. And so this is actually super cool because we can actually take videos of planets over time. You can just take a lot of data and then compile it into a video. And it's right now it's kind of rare to find systems that we actually can do this for, because it really requires the planets to be very far away from their star. So here the star is at the center of that little mask that it has like a little yellow star dot in it. And you can see that the scaling is 20 AU. So 1 AU is an astronomical unit, which is the distance from the Earth to the Sun. And so the closest planet to the star is something like 20 times the distance of the Earth to the Sun. For reference, Pluto is 40 AU from the Sun, so it's about halfway from the Sun to Pluto. And then you have a lot that are like way farther out than even Pluto is. So hopefully as we kind of continue over time, we'll improve technology so that we're able to see kind of closer in planets and have like a smaller mask and not so much noise towards the center. And one of the really cool missions that's coming up that is going to be able to do direct imaging is called WFIRST. So it's planned for launch in the mid-2020s. It's going to be a 6-year mission. And one of the really cool things that it's going to do is instead of having this coronagraph inside of the instrument, it's going to have, hopefully, when they get the technology sorted out, it's going to have this star shade, which is actually external to the telescope. So they're going to launch up this cool, like, flower-looking thing that will block out the star's light. and then you'll be able to resolve the planets around it. And so by having this sort of external system, you actually avoid a lot of the problems that you can get with optics within a telescope if you have a coronagraph. I actually did check this image policy. It's actually okay for me to use this, just so you know. Yeah, so I think that this is really going to be the future. Pretty soon we're going to be actually images of exoplanets, which I am so excited for. We already have some, but we're going to get even more, and more of the kind of inner ones. And so I will finish with a conclusion. So in conclusion, this is like really my takeaways. Exoplanets are heck cool, extremely rad, the absolute best, and that's all. Take it easy.
That was an amazing talk by graduate student Malena Rice on exoplanets and all these cool missions studying exoplanets. So yeah, we have time for Q&A. So Joel is actually going to be running around with the mic this time. Where's Joel? Oh, there's Joel. Joel has the mic. So Malena and I are going to trade one and Joel will have the other. So let's have a question. Questions? Right here, Milo.
I've got two quick questions. The first one is there a pattern in the geometry of rotation? I'm sorry, can everybody hear me? Is there a pattern to the geometry of rotation in the exoplanets in our galaxy, and does that give us any intuition about the formation of our galaxy?
So the question was, is there a pattern in the rotation of exoplanets?
So are they all kind of aligned the same way?
Yes, so are they all aligned in the same way? They are not, and as far as I know, I don't think we actually have any sort of correlations that we've found. So the solar system is actually not aligned with the plane of the galaxy. The galaxy is sort of like a disc shape, so it's sort of this flattened spiral shape, and the solar system is not aligned with that disc. So the exoplanetary systems are expected to be a kind of, on average, kind of like a random orientation. So that's not really something we have a correlation with.
Just one last question. For the large planets that are orbiting super close to their stars, do they behave, do we believe that some of them behave like our moon, where one side is always facing the sun or the star, and so there is a potential for us to explore the other side?
Repeat the last sentence.
So just like our moon always faces towards the Earth with one side, these super planets that are orbiting incredibly close to these stars, is one side potentially always facing the stars so that the opposite side is cool enough in order to land the craft on it?
Yeah, so the phenomenon that you're talking about is called tidal locking, and that is true for a lot of the exoplanets that are very close to their host stars. So that's true for a lot of the hot Jupiters and a lot of the super Earths that are very close in. And effectively what that means is just that one side of the planet is experiencing day all the time, so it never has nighttime, it's always facing the star, and then the other side is always experiencing night, so it is never facing the star. So what that means is that you'll get these sort of differences in climate in general across the two sides. So one of the sides is always going to be really hot, and the other side will be really cool, and so there are kind of implications as to the general circulation that you'll get of that planet just because of the completely different heating on the two sides.
Can I just ask, I really hate to be a buzzkill, but can I just ask the people in the back to just be a smidge quieter? Because I can't hear the questions and the answers, and I know some people really do want to hear these. So, anyway, yeah, can we have, thanks, yeah. Just a smidge quieter, guys. Okay, another question. Joel, Mike. Back here, Joel.
Is there an underestimate for what fraction of stars have planets around them?
Yeah, so right now the question was, is there a lower estimate, I believe, for what fraction of stars we believe have planets around them? We actually, I guess the short answer is we think probably almost all stars. So it's going to be pretty close to 100% actually. And we haven't been able to find all of them because we've mostly been looking at the transit method, which is kind of biased against a lot of different systems that don't have planets really close in. But we expect that really almost all stars should have planets.
Another question.
The Kepler telescope looked at one spot for a long time to catch, transits, but the TESS seems to move rapidly. How can it catch these